We feel very fortunate to have gotten Jeff Solar to come today. He's a principal scientist for Solar Environmental. In his role, he advises policymakers and provides technical assistance for environmental policy development related to human health effects associated with waterborne and water-related contaminants. After talking to Jeff when we were courting him to come, I hung up the phone and I said to Don, that's the guy. That's the guy we need. So again, feel very fortunate that Jeff had time in his schedule. And with no further ado, Jeff.
So thank you very much for the invitation. And I also want to note, thank you very much for preparing all the 200 and whatever pages of supporting material. Because here's the thing. I'm a guy who knows a lot about risk and a lot about water and risk and human health risk, but I don't know very much about produce. And so I might be the only one in the room that actually read all 220 some pages in order to prepare for this. So I have, maybe there's a couple others, but I appreciated it. And what you'll see is that I stole a bunch of the material that's in that packet for my presentation. So if it looks familiar, you can take credit for it right now. So we've heard a lot, we've heard the word risk a lot so far over the course of the day. And really what I want to do over the next half an hour is I want to add some context to that. Like, what are we talking about? What's it mean? And where are we coming from when we talk about it? So I want to do, my presentation's broken into 3 parts. I want to talk a little bit about, like, what is risk analysis, okay? I want to talk about some risk considerations for produce safety. And then I want to talk about some perspectives, my perspectives on microbial risks of the produce safety rule standards for agricultural water. And specifically, I want to talk about the numeric standards that we talked about, and then this whole concept of the level of public health protection associated with it. Sound good? All right. So risk analysis. When we think about risk analysis, typically we think about risk in 3 different components, okay? One's risk assessment. That's a lot of what I do. This is real technical information where we gather a whole bunch of information together and we try to make some sense out of it, okay? One's risk communication. This is where we're taking all this information and maybe the governmental agencies are giving it to the people who are using it, or maybe it's the users who are giving it back to the agencies. And then there's risk management, okay? So risk management is about the policy setting. So policy setting is inherently a governmental activity. I was on a call the other day and somebody said to me, well, like, what is it that you do when you set policy? And I'm like, I don't set policy. Okay, so setting policy is inherently governmental activity. This is what governmental agencies do. And the thing about risk management is this. It's really complicated. Okay, this is something that I stole off the web from somewhere. And if anybody in the room understands this, I want to know about it, okay? But the idea here, though, is that when agencies are forced to do risk management, they have to take into account a ton of different factors, okay? They have to take into account factors that you don't know about, factors that you don't understand. They might even take into account the factor that you think is most important, or they might not. But when it comes to something like produce safety, you might look at the rule, you might say, I don't like that rule. And you might say, I don't like that rule because it's not stringent enough. Person next to you might say, I don't like that rule because it's too stringent. The person next to them might say, I don't like that rule because it's going to cost me too much money. Scientists in the room might say, I don't like that rule because it doesn't take into account the science that I think is most important enough, okay? So the thing about risk management is that the people who are charged to do risk management have a terrible job. Okay, they have to take all that stuff, and then they have to balance all of it and find a way, find a path forward. Okay, and I think that that's really important because when we're faced with, I've been involved in a number of different water regulations, from the groundwater rule, 2012 recreational water criteria with the EPA. There's never a rule that everybody likes, and if there is, something's wrong. Okay, so it's important to understand. I'm not saying that you have to change the way you feel about anything or the way you think about it, but it is important to understand what all the different drivers are. And then the question is, how can the drivers that are most important to you, how can you most effectively communicate those so you can influence the risk management decision, okay? So risk assessment is typically broken into a couple different steps. And so I just want to break it down really simply, and I'm going to take the previous quote to heart, and I'm going to see if I can explain this complicated topic really simply, and you can tell me if you think I understand it when we're done, okay? So the first question is, what hazards are we concerned about? And there's a couple different ways that we can think about what hazards that we could care about. One is like, well, what outbreaks have occurred, okay? And we could think about what outbreaks have occurred with produce, or we could say FDA has this big program where there's surveillance data, health surveillance data. So what outbreaks occur in the United States? So if you look at outbreak data, that could give you one idea of what hazards or pathogens. So pathogens are microbes that make you sick. And another way to do it is to say, well, what illnesses occur in the community, especially when we're thinking about water. Now, why would that be important? Well, if you're sick, you're shedding pathogens into the waste stream, into the water, and then that water gets treated and then discharged to a surface water body, okay? And I can tell you that not all of the pathogens get removed, okay? And so there's a vector, there's a stream. And so if we say, okay, so what are people getting sick from? That's likely a way that you could go about figuring out which pathogens you care about in the water that you're using for agricultural purposes, okay? No matter how you do that, you come up with a couple bacteria, a couple protozoans, those are Cryptosporidium and Giardia, and a couple viruses. Now, viruses are really important because E. coli is not a very good indicator for viruses. I skipped ahead. I wasn't supposed to say that, but there's a secret for you, okay? The next thing we think about risk is this. It was like, well, risk to what? Risk of what? And there's a couple different endpoints. One endpoint is infection. So are people getting infected? Okay, and an example here is that the use of recycled water for potable purposes in the US is moving toward a benchmark level or a tolerable level of risk of 1 infection per 10,000 people per year. That's like a drinking water level. Okay, that's an infection. Another possible health endpoint is illness. So recreational waters in the United States now are based on a level of protection of 32 or 36, gastrointestinal or GI illnesses per 1,000 recreators or 1,000 recreation events. Okay, anybody who's paying attention might say 32 or 36, that seems kind of crazy, but that's just the way that the regulation, was derived, okay? Another possibility is to do, we've heard about health burden, and we saw this DALI earlier today, and the WHO, there's WHO guidelines for safe drinking water, set at 10 to the minus 6, so this is 1 per million, which is 10 to the minus 6, DALIs per person per year. And this health burden approach has some real advantages. That is that it can take advantage of how severe an illness is. So if a healthy adult gets sick and misses work for a day or two, even if you feel like you're gonna die, okay, you get better and you get back to work, that's really different in terms of a health burden than if an immunocompromised individual or a child gets a long-term illness and is sick for months, spends months in the hospital, okay? So this approach has the ability to take care of that. It can also focus on the actual outcomes and it can help support priority setting, but the calculations can be a little bit subjective, and it's also pretty darn difficult to explain what it means. Like, who can explain to me what 10 to the minus 6 DALIs means, right? So you got everybody in the room saying you want something simpler. Well, DALIs is not necessarily simpler, but it is a potential health endpoint, okay? Uh-oh. Okay, so the next thing when we think about risk assessment, again, is the root or roots of contamination or the roots of exposure. So how do people get exposed to the pathogens that make them sick? Well, produce commodities are susceptible to microbial hazards before, during, and after harvest, right? And there's a number of possible routes of exposure. And the focus right here is just on water, and I'm gonna be focusing really on the pre-harvest time. Okay, we talked a little bit about post-harvest time and some die-off, but really my focus is going to be on harvest. Now, of course, there are other potential exposures, routes of exposures that could occur that could get people ill through produce, but for this particular talk, I'm going to focus on water. So if we think about running a risk assessment or conducting a risk assessment, there's a couple different factors that we would have to consider. So, for example, if we wanted to say what's the risk of either a risk assessment or what's the exposure, we'd have to think about a couple different things. So for example, what's the water source? We talked about that earlier. I think 8 of the 10 groups mentioned that the source was important, right? Another one that could be important was like, well, what's the application method of the water? Is it a spray system? Is it subsurface irrigation? It's really different, the amount of water that would end up on the crop and potentially end up with a consumer, right? The timing, we mentioned that in the last group, so I won't get into that. What's the crop? How many servings per acre? What's the percentage of acreage that's irrigated? What percent of the water hits the edible portion of the crop? Then there's also die-off in the field. There's also die-off or growth during storage. And then further down the line, there's potential for cross-contamination. And then if we think about, if we actually wanted to characterize the risk, we have to think about consumption. So how many milliliters of water does an individual ingest from a particular crop? Does that all make conceptual sense? Okay. This is a really nice graph that I did steal from the materials. I thought this was actually really nice. This is just a qualitative summary of exposure from least exposure to most exposure, looking at some of the factors that I just laid out. So I think something like this is actually pretty helpful to kind of get your mind around. If you're more visual oriented than word oriented, this kind of gives you an idea, So like, what are some of the least as opposed to most? Very qualitative kind of assessment. Well, the public drinking water is less. There's less likelihood of contamination than groundwater or surface water or unprotected surface water from runoff, and the same thing with the contact and the commodity. So I think that this kind of thing, this kind of graphic, can visually it can be helpful for understanding the potential level of exposure that can occur through this route of exposure. And I think these slides are all going to will be available online. I think that's what it says. So if you wanted these, you can have these. So then the last piece of this is risk characterization. So what is risk characterization? Okay, so what risk characterization is it's a mathematical approach to integrate and synthesize information to convey the nature, existence, and extent of human health effects. So it's a mathematical modeling approach. It should be complete, it should be informative, and it should be useful for decision makers. And then there's this thing that I really like called TCCR. So whenever anybody does a risk characterization, it should be transparent. That means you should understand it. It should be clear. It should be consistent. I actually really like concise too, myself. And it should be reasonable, okay? And these analyses can vary in complexity, anywhere from qualitative to relative to quantitative. And what I mean by relative is, so qualitative is kind of low risk, kind of high risk, really high risk, okay? Relative is, this scenario is riskier than that scenario, and this scenario is much riskier than that scenario. And quantitative, it gives you a number, okay? The risk of illness is one per thousand portions, okay? So here's some perspectives on the microbial risk. So now you have a background. Now you understand the field of risk analysis, okay? And here's just some perspectives on the produce safety for agricultural water. And I just want to do two things. How am I doing on time? I'm halfway through. Halfway through. Good. Perfect. Okay, good. So I want to talk a little bit about the numeric standards, and this was done earlier for me, so I'll be able to go through this. I want to talk a little bit about the basis, which is the EPA's REC criteria, and then I want to talk a little bit about the public health protection, and then this concept of same level of public health protection. So the numeric. So I have some screenshots. I don't know how many of you have actually gone through the Federal Register and read all this stuff. There's some really good and important stuff in there, and so I have some screenshots that I hope will help you later if you ever need to go back to refer to this. And I promise I won't read it all word for word. Okay. So there's some really important stuff in here. So first of all, the rule says that it establishes these science-based minimum standards for the safe growing, harvesting, packing of produce on farms, and it's based on a qualitative risk assessment. And one of the major areas was agricultural water. So one thing that's really important about the language that's in here is it says that, and I think that you all have picked up on this, it must be safe and adequate, safe and of adequate sanitary quality for its intended use. So I think we heard at least 3 times today. What does that mean? 15 minutes left, got it. Another thing that it does is that it requires specific analytical testing, and I'm not going to go into that because we just spent the half an hour before that, and then it specifies these numeric standards as a geometric mean of 126 with what amounts to a 90th percentile of a log normal distribution of 410. Okay, so I will tell you that this whole idea of a 90th percentile instead of a single sample maximum is your friend. Okay, so the single sample maximum in the recreational water field was a real problem that has recently been resolved in the 2012 criteria. So you should be grateful that this specifies it as a percentile of a distribution rather than a never to exceed number. Okay, because that happens. These indicator bacteria vary widely in water, and you can have a perfectly reasonable distribution, and from time to time you just get a super high value. Okay, and it should not be that one super high value in a long time becomes a problem for you. Okay, and so this 90th percentile does resolve that, and so that's actually quite good. Okay, so where do these numbers come from? Okay, so earlier today we heard that there were kind of two places where values were drawn from. One was the WHO guidance, one was the 2012 criteria. So these 2012 criteria, I was involved supporting EPA when these were derived, so I'm very familiar with this. And so this comes from the 2012 criteria document. And what you see is that there's two different sets of criteria values for different illness levels. So this is really important, okay? These criteria are risk-based, okay? This set of criteria is based on an estimated illness rate of 36 illnesses per thousand primary contact recreators or 1,000 recreation events, and they're using E. coli. So a couple things. E. coli is a fecal indicator bacteria. It generally does not make people sick, although there are strains of E. coli that make people sick, but mostly it's not. It's an indicator of fecal contamination, okay? And then there's a geometric mean and a standard deviation. So when these were developed, they were developed based on very specific conditions and for very specific assumptions. And when these were developed, they were that illness level, that 36 per thousand, is for recreation or swimming in both fresh and marine waters. They were derived from epidemiological studies that were conducted around the United States. Okay, those epidemiological sites were specifically selected because they were waters that were impacted by treated municipal wastewater effluent. Okay, this is second, not 100%, but mostly secondary treated and disinfected either with chlorine or UV disinfection waters, okay? And that because this level of protection is explicit in the 2012 criteria, there's a whole section of the document that talks about alternative criteria. So I might have a water body, for example, that's impacted by gulls and not humans, and the gull risk is less on a per indicator basis than humans, and then therefore I could have an alternative set of criteria that could be derived via epidemiology, quantitative microbial risk assessment, or also it's possible there's approaches laid out there that describe alternative microbial methods to enumerate the fecal indicator bacteria of interest. Now, E. coli are imperfect indicators, okay? This is a slide that I stole from page 169. This is Yakov Pachevsky's work, okay, where they looked and they said the number of significant relationships between a coliform indicator and pathogens. And for each of these different bacterial pathogens, what they found is that E. coli was an imperfect indicator, okay? But E. coli does what it does. I mean, it may not be perfect. There's not going to be a perfect correlation between a fecal indicator bacteria and a pathogen in every sample, but it does, historically, it does a good job for its intended purpose. Okay, with that in mind, though, especially to FDA's credit, they mentioned that they evaluated that. They found that the scientific rigor underlying the criteria to be sufficient to rely on their thinking for agricultural water, and that they could use the criteria, the recreational water criteria, as a starting point. Okay, and that that's what both those slides. So these are the two sections out of the Federal Register where it talks about that it's not actually relying on that as the same risk level, but actually they're using the scientific basis as a starting point. So I think that they're being very transparent about the choices that they're making. You may not agree with them, but it's transparent, and it does meet the criteria that I talked about. So what do we know about the risk that is associated with the numeric standards? Okay, so there were two different assessments that I found. One was a qualitative assessment, and one was a more quantitative assessment. So the qualitative assessment, this is what I told you before. So what this did is it looked at a number of different a number of different crops, looked at a number of different factors such as the likelihood of exposure, the severity of the hazard, and then the risk of illness. And what this shows is that the ones that are light, the risk is lower than the ones in the light gray, and the risk in the ones in the light gray is lower than the ones in the dark gray. Did I get that right? Okay, so this is a qualitative assessment. Lower, medium, high. Okay, so it kind of gives you an idea. And then the second assessment that was conducted, that I found, was this quantitative risk assessment. And so this quantitative assessment was evaluating what the risk might be associated with the numeric standards. And in this case, what was done. So remember, back to the beginning of my talk, I said that there's a couple different components of a risk assessment, right? So in this case, they looked at the hazard was this is a pathogenic E. coli. Okay, so it's a kind of E. coli that does make people sick. The crop was lettuce. The exposure was an irrigation water via an overhead sprinkler. And then they looked at a wide range of water qualities. And the question was, what's the relative level of risk, or what's the risk associated with water, a varying range of water qualities? And then the health endpoints that they looked at was probability of illness, and then a DALY-based health burden approach. And this is the front page of that document. And this was the quantitative risk assessment used to support the proposed produce rule. So this is pretty interesting if anybody likes graphs and data. Okay, I don't know how many of you do, but I do. Okay, so this is really interesting. So essentially what there is there's 1, 2, 3, 4. There's 6 different water qualities that are represented here. One water quality is basically use of municipal water, which basically has 0 E. coli. So the E. coli increases as we go along the horizontal axis. Okay. That's represented by C. D is represented by within the proposed monitoring limits. And then B was a moderate exceedance of the proposed monitoring limits. There were 2 other farms, F and E, that had higher contamination. And then you see this thing goes from 700 and it goes all the way up to 10,000. And A is gross contamination. And so the question is that when you run a risk assessment with using the water quality and a whole bunch of assumptions that are built into it, what's the predicted level of risk? And so what this shows then is that as the water quality gets worse, as it goes from 0 to something very high, that the predicted number of illnesses per acre would increase. And so, I find this actually pretty interesting, because when you look at the data, what you see is that it's really low, it's pretty low, and then it starts to jump up, and then it goes up really high. And well, probably not quite as magic as that, because this is actually, 50, this is 200, that's 700, this is 10,000. So it's not really that surprising that the numbers jump from 1 to 546. But nevertheless, this is an idea of a quantitative risk assessment that one might conduct, and that was actually conducted to illustrate what the potential risk associated with the proposed rule is. Does that more or less make sense, even to people who don't like data so much? Maybe not. Maybe not. Okay. So the last thing that I want to mention, and this has been mentioned previously, is that there's now a brand new document out that talks about the same level of public health protection. So there are alternatives that if one could demonstrate the same level of public health protection or better, that alternatives are available. And again, this is spelled out in the Federal Register, and here's the documentation for it. And these same slides, these same bullet points were provided earlier today. So these are the main factors that one would consider. Do the data support a determination of the same level of public health protection? Are there any unique considerations? Was the evaluation conducted by somebody who knew what they were doing? And is it properly documented? So there's not a specific level of, like you must meet 1 per 1,000 per year, but basically what it's saying is that if you can meet the same level of public health protection, then an alternative could be proposed. So here's my last slide, and you've seen this before. And so I'm hoping that I was able to add a little bit of perspective and a little bit of clarity to this whole idea of risk associated with agricultural water and produce. I'll be interested to find out from some of you during the break if I was successful or not. But I do hope, if nothing else, that you'll think about this framework and think about this framework in the context of what your comments are and in the context of the job that FDA is trying to do also. And so there's a lot of different varying perspectives. And that I think in order for you to be effective in what is most important to you, that hopefully this context will be helpful. So with that, I'll conclude. And if you have any questions, apparently I have about 5 minutes to answer them. So thank you very much for your attention.
It's actually not a question, Jeff, because you did an excellent job, I think. But maybe go back to the definition of hazard assessment, because that's also relevant for the next breakout group, where a lot of the hazards assessment discussions are about what are the pathogens that are causing disease, and that's often very relevant. But I think for the next discussions, it's also important to realize that it can also be an event that creates a risk, causes an outbreak, or more related to the HACCP type of risk assessment, where you're not so much looking at what is the pathogen, but what is the event failure of a pasteurization process. So I think that's also important to realize that that's also a way to define hazards, and it's more tangible maybe when you think about a physical system.
I think that's a great comment. That I think that outbreaks occur, but outbreaks don't just occur every day. Outbreaks occur because something went wrong. And so we like to think of these as hazardous events. Maybe it was a precipitation event that caused some runoff. We think about what happened in Milwaukee in 1992, 1993. This was a snowmelt event. It was a runoff event where there happened to be a bunch of cow poop that came into, and at the same time there was a coincident water treatment failure. Okay, so I think the idea of these hazardous events is really important. And I think you're right about that. In terms of illnesses in the community, this is something that you may not be aware of. This is really interesting data in my view. So these are data from the CDC. They were originally published by Paul Mead in 1999 and then updated by Scallon in 2010 or 2011. I can't quite remember. But what this shows is that there are 38.5 million illnesses known from known pathogens in the U.S. per year, and of those, 13.8 million are foodborne. Okay, so of those 13.8 million, 9.3 million are viral, with 9.2 of that 9.3 being from norovirus, Norwalk-like viruses, 350,000 from parasites, and 4.2 million from bacteria. So when you start to think about the kinds of microbes that you're probably interested in terms of foodborne contamination, I think that this is an interesting way to be looking at it. I mean, the other thing, in fact, Kevin Oshima and I were talking about this earlier today. The other thing that's interesting about this is that when you look at the outbreaks, actually you kind of see a different story. And so, like, if you look at all the outbreaks that have occurred, this is based on surveillance data from 1996 to 2014. There were 17,000 people ill, but most of them were from bacteria. So what's the story there? Is it because there's something different going on, or is it because we're not actually finding the viral illnesses, or is it because the bacteria are actually reported and the viruses are not? There's a lot of questions, and so I think that to get a good picture of it, it actually makes sense to look at it from a couple different ways. I guess kind of my view.